This video presents about the advanced data structure concept, that is AVL trees. We shall cover about what is AVL tree, and similarly what are the operations that can be performed on the AVL tree, that is how we can insert the node within the AVL tree and how we can delete a node within the AVL tree, and so on. So coming to the AVL tree, it is basically it is also the binary search tree that uses the modified add and remove operations to stay balanced as its elements change. Whenever you are adding the new node or whenever you are deleting a certain node in the AVL tree, there are certain modifications which has to be done based on certain criteria. So AVL tree can be said as it is self-balancing binary search tree. And it was invented in the year 1962 by Adelson, Welsky, and Landis. That is how the name has come, AVL tree. And the properties of the AVL tree, which includes subtrees of every node differ in height by at most one level. And every subtree that you consider is also an AVL tree. In the AVL trees, balance factor of each node is maybe 0 or 1 or -1. So in brief, we can say AVL tree, it is also the binary search tree. So when I say the binary search tree, the properties of the binary search tree remains the same. That is, if we consider a kind of the elements which are being provided, some n number of the keys are being provided, and you have to arrange this kind of the elements such that the root and similarly whatever the elements that you place within the left subtree should be less than this kind of the root, and whatever the elements or nodes that you place towards to the right should be greater than this node. What does this mean? Like take for example, you are being provided with the elements. So consider you are being provided with the nodes or elements or keys, nodes, assuming like the nodes. So consider the nodes which are being given as an input 20, 10, and similarly 30, and as well as 40. So these are the nodes which are being provided. And to find how many number of binary search trees which can be generated for n equal to 4, that can be identified by the Catalan number. That is not the part of the AVL tree. This is only because we are moving to the advanced part, that is AVL tree. So here, if you consider the given input nodes to be equal to 4 nodes, how can we arrange? I'm concerning about the binary search tree. So within the binary search tree, that is like take for example, if you start with the node to be equal to, that is 20. The elements that you place towards to the left should be less than the root node. That is 10 should be placed as the left node, and similarly that is 30, and similarly we have the node to be equal to 40. So take any kind of the subtree. That is, if you consider 30, that is the root node is less because it is a right shade. And similarly, if you consider 40, the root node, that is it is less than this kind of the 40 because it is the right shade. And there is a factor which is involved in the AVL tree. That is, AVL tree is also the binary search tree. The properties remains the same, but whenever you are adding and whenever you are deleting, or whenever you take a certain kind of the AVL tree, it should have certain kind of the factor. That is, balance factor has to be maintained. And what do you mean by the balance factor? That is, I'll provide with an examples of what is this balance factor. So balance factor should be either -1 or 0 or 1. These are the permitted values or levels for the AVL tree. So AVL tree makes sure that the tree remains balanced as we go on inserting the new nodes or deleting the existing nodes. That is, whenever there is an AVL tree that is present, and when you are adding the new node, then you have to maintain the balance factor. Similarly, whenever you are deleting a node, by deleting this kind of the node within the AVL tree, and if it changes, you have to rearrange such that the balance factor of the AVL tree should be either -1 of that kind of the nodes, that is -1, 0 or 1. And the examples of self-balancing tree, what do you mean by the self-balancing tree? That is, whenever you are adding a node or deleting a node, then it should be self-balanced. What do you mean by the self-balanced? That is, it should be the balance factor should be either -1 or 0 or 1. Then only we can say it is a self-balancing tree. And some of the examples that can be given for the self-balancing tree are, that is AVL trees, red-black trees, splay trees, and B trees. These are some of the examples where we can say about the self-balancing tree. At any stage, the balance factor remains for the case of the examples which are being considered. So the basic idea is when the nodes are added to or removed from the tree, if the tree becomes unbalanced, what do you mean by the balanced and what do you mean by the unbalanced? That will be explained with an examples. So if you are adding or upon deleting a kind of the node, and if it becomes the unbalanced tree, then you have to repair this tree such that the balance is being restored. And the balance factor, that is B of every node, is being given by within the range, that is -1 less than or equal to B less than or equal to 1. That is, B ranges between -1 to 1. That is, the possible values of the balance factor are -1, 0, and 1. And if you consider any kind of the tree, then the possibilities, that is, whenever you are adding a node or whenever you are deleting a node, there are three possibilities. That is, the height of the left subtree is less than the right subtree. That is first possible scenario. The second scenario, both the things may be balanced. That is, both the heights are balanced. Both the heights are same. Left subtree is same as compared with the case of the right subtree in the second case. And in the third case, that is, the height of this subtree, left subtree, is more as compared with the right subtree, which is being denoted by H and similarly H minus 1. H minus 1, that is, it is less height as compared with the case of the left subtree. So these are the three possibilities at any case whenever you are adding a node or whenever you are deleting a node to the binary search tree. That is, either the left subtree may be higher, that is height is more, or the right subtree's height is more, or both the heights are same, that is left subtree height and as well as the right subtree is same. These are the three possibilities. So whenever you are considering the unbalanced tree to the balanced tree, then you have to keep this into the factor. And if it is unbalanced, then you have to modify, you have to repair the tree. And how to repair the tree, that will be discussed in the later part within this slide. That is, we have to perform LL rotations, RL rotations, RR rotations, and similarly RL rotations, depending upon which one is higher. And to start with what is, at least we need to identify whether it belongs to the AVL tree or not. So if you recall about what I've said related to the AVL tree, it is also the binary search tree. AVL tree is also the binary search tree, and within the AVL tree, that is, the height of any kind of the node should be between -1, 0, and 1. Only these three possible values. And if it height exceeds this range, then we can say like it is not the AVL tree. Now the further slides goes on in such a way that we have to identify whether it is AVL tree or not. As I mentioned, the two parts. That is, the first one is it is the binary search tree. So if I say about the AVL tree, it should be the binary search tree. The property of the binary search tree remains the same. That is, whenever you consider the root, the nodes which you place towards to the left should be less than this kind of the root, and the nodes that you place towards to the right should be greater than this kind of the node. That is the property of the binary search tree. So here, according to this case, the first property space about the binary search tree. And the next one is the height, that is the balance factor. Should be either -1 or 0 or 1. The height of any kind of your node should be either -1 or 0 or 1. At the initial case, I'm not considering about the balancing factor. By just looking at this kind of the tree diagram itself, we have to identify whether it is an AVL tree or not. So the first thing, what do you mean by the height balancing? That will be explained in the further next slides. So here, when you consider about the binary search tree, the first property remains. That is, if you consider the root as 10, so the element that is placed towards the left should be less than this root, and the element that you place or the node that you place towards to the right should be greater than this kind of the node. So in such case, this is the property of the binary search tree satisfies. And is there any height unbalanced? What do you mean by the height unbalanced? This is like, for example, the level 1, and similarly this is at your level 2. Then in such cases, the at this kind of the instance, the root contains 2 children. So the height is balanced, and that is how we can say it is an AVL tree. So this satisfies the property of the binary search tree, and similarly the height of 2 subtrees of every node differ by 1. So here we can say that is the height, the left child and some the right child, the heights are same, and that is the purpose we can say this is an AVL tree. And what is, or how does the not AVL tree, I mean AVL tree is not isn't considered, that will be explained with an example. So here you can observe within the case of the property of the binary search tree. So 5 is being kept as an left subtree, I mean left node, left child, that is satisfied. And if you consider the 15, that is 15 is greater than the root, that is also satisfied. 20 is greater than 15 and as well as 10, and the property of the binary search tree is being satisfied. And when you consider about the height, it should be either 1 level below or 1 level above. In the previous example, that is in the previous example, if you consider this kind of the height, which are at the same level, that is same level, and the height is also at the same, and that is the purpose. The previous was the AVL tree, and now this is also an AVL tree. It differs not more than 1 level. So this is also an AVL tree. Why? Because even though this kind of this is considered, this is your level 1 and similarly level 2 and similarly level 3. It does not differ not more than 1 level. This is 1 level, this is accepted. And that is how we can say this kind of the tree is an AVL tree. And consider about this kind of the tree diagram, whether it is an AVL tree or not. As I mentioned, the AVL tree, it should satisfy the property of the binary search tree. Take any node, like take for example something like 17. So 17, it is greater than the root node, that is 15, and also greater than the parent root node, that is 10, that is satisfied. Take any node in the tree, if it satisfies the binary search property, then go for your height part. So here 25 is greater than 20 as well as 15 as well as 10. So take any node that is present in your right subtree, it should be greater than the root node. The property has been satisfied. And similarly, if you consider about the part of your 5 and similarly 7. So 7 is less than 10, the properties of the binary search tree is satisfied. So 7 is greater than 5. That is how the right child is being kept for 5. So it is satisfied. And whereas if you consider the level, like take for example, this is at your level 1 and level 2 and similarly level 3, to 1 level down or to 1 level up, we can satisfy, but not more than 1 level. So if you observe, the leaf node of this kind of your left child is equal to 7. So to 1 level down, up to this, it has been satisfied, but not beyond 1 level more. So you are exceeding. And that is how we can say, of course, it is the binary search tree, but height is not the binary search tree. Why? Up to this level, we can say it is a AVL tree, but 1 level beyond this one, we cannot say it is the AVL tree. And that is how we can say this is not an AVL tree. Now you can easily guess whether it is an AVL tree or not. First, you have to identify whether the property of the binary search tree satisfies. take any node within the case of your the left subtree, and it should be less than the root node. So it is less than 12, 5 is less than 12, 9 is less than 12, 4 is less than 12, 2 is less than 12. Take at any subtree, like take for example 8, 5, 9. So 5 is less than 8, that is satisfied. 9 is greater than 8, that is also satisfied. And that is how it is being kept as the right child of the node 8. And similarly, go to the right subtree. So 18 is greater than 12, 17 is also greater than 12, and 17 is being kept as an left child of node 18. The property of the binary search tree is being satisfied. But when you consider about your the height, that is okay, one level down or one level up. So up to this one we can satisfy by, because the last leaf node of your the right subtree is up to this level. One level down we can satisfy, but not more than this. So this node 2 does not satisfy the property of the AVL tree, and that is so we can say it is not an AVL tree. Similarly, you can easily guess whether it is an AVL tree or not. So here first you have to identify whether it is a binary search tree or not. So take any element 8, 5, 11, it is less than the root node, and 17, 18 it is also greater than the root node, and that is how the property of the binary search tree is being satisfied. But considering about your the height, that is take within the case of your, this is your level 1, level 2, and similarly level 3, and the leaf nodes are being present at this kind of your level. One level down we can say, that is if you have something like take 13. So 13, one level down we can say it is also the binary tree. But further, once again, like take for example this is 14, and further if you have one more node that you attach to 14, and then we can say it is not the property of your the AVL tree, because when you consider the leaf node at this level, it is okay. One level down it is okay, but further one level down we can say it is not the AVL tree. But as far as concerned this kind of your the diagram, so considering about this kind of your the diagram, since height is not, there is no the balance factor does not exceed the range -1, 0, 1, and that is how we can say this is an AVL tree. So you can easily guess that is it is an AVL tree. First you have to identify whether it is a property of the binary search tree satisfies or not. If it satisfies, then go for checking whether the height is balanced. So what is the last leaf node that is present at your right subtree? That is 14. One level down we can say it is an AVL tree. So that is how 2 and 6 are being placed, and it is an AVL tree. If you consider this diagram, you can easily say it is, we can say like it is not the AVL tree. Why? Because this is your last leaf node that is present, and similarly one level down up to this one we can include the nodes, but further beyond this one we cannot include the node, and one is being included far beyond the last leaf node towards the right subtree, and that is how we can say it is not an AVL tree. So that is some kind of the brute force method to identify whether it is the AVL tree or not, to guess at least at the initial stages. Now consider about the technical way of identifying whether it is an AVL tree or not. So here, as I mentioned, the certain parameters related to the AVL tree. That is AVL tree, it is also the binary search tree, and it should maintain certain kind of the balance factor. Every node should maintain certain kind of the balance factor. That is, the balance factor of a particular tree or the subtree is being given by height of a left subtree minus height of the right subtree. In AVL tree, no nodes two child subtrees differ in height by more than 1. That is, it can be either one level down or one level up, but not beyond this one. So the balance factor values can range, that is -1 less than or equal to 0, b less than or equal to 1. That is, it can be either -1, 0, 1. And if the balance factor of any node is 1, what does it indicate? It means that left subtree is one level higher. As I mentioned, the three possibilities of the trees, that is subtrees, that is left subtree is high, that is more height as compared with the right subtree, or the right subtree is height is more as compared with left subtree, or the both the things, that is both the heights of your the left subtree and as well as the right subtree are same. So here when I say about the balance factor of any node which is equal to 1, then it indicates the left subtree is one level higher than the right subtree. The same fashion, if the balance factor, what is actually the balance factor? The balance factor is equal to height of left subtree minus height of right subtree. What does this indicates? That will be provided with an example in your continuation part. So understand, if the balance factor is equal to 1, then it indicates the left subtree is one level higher. And if the balance factor of any node is 0, then it means the left subtree and the right subtree contain equal height. And if the balance factor of any node is -1, then it means that the left subtree is one level lower than the right subtree. So here given the height of, the balance factor of certain kind of your the node is given by height of left subtree minus height of right subtree. What does this indicates? How to find the balance factor of any kind of your the node? So here the balance factor of 8 is we need to consider we are starting from the leaf nodes. So height of your the the balance factor of your the 8. If you need to identify what is the balance factor of this kind of your the node. So balance factor of 8 is given as height of your the left subtree. That is, for 8, are there any left subtree and similarly the right subtrees, since it is the leaf node. Since it is the leaf node, so leaf node, when I say about the leaf node, it does not contain either the left child or the right child. So the height of your the left child, height of your the left subtree of your 8 will be equal to 0, and height of your the right subtree of 8 will be equal to 0. So balance factor of the node 8 is being kept as 0. And similarly, if you consider the balance factor of your the node 12, since it does not contain any children, no subtrees for your no left subtree or right subtree will be present. So that is how height of balance factor of 12 is being given as 0. So all the leaf nodes, the balance factor is being kept as 0. And coming to finding the balance factor of certain kind of your the node, like take for example the parent node, that is 10. So how to identify the balance factor of the node 10? That is, which has been given by height of the left. If you recall about the formula for the finding the balance factor. So balance factor of any kind of your the node is given as height of the left subtree minus height of your the right subtree. And what does this height indicates? That is, when you consider the node 10, that is, there is one node, that is 8 to the left subtree. There is one node towards to the right subtree. So that is how height of your the left subtree, that is 10, is equal to 1, and height of your the right subtree, there is one node that is connected as a right child for the node 10, that is 1 minus 1, that will be equal to 0. So here the balance factor of your the node 10 is equal to 0. In the same fashion, you can also identify what is the balance factor of the 20, height of your the left subtree. That is, there is one node, that is 1 minus, and then we have node 25 towards to the right, that is 1 minus 1, that will be equal to 0. In the same fashion, that is, if you need to find the balance factor of your the 15. So what is the height of your the left subtree? There are two levels. That is, this is your height 1, and this is your height 2. So there are two levels which are being present. So height of your the left subtree is equal to 2, and whereas height of your the right subtree is equal to 2. So 2 minus 2, that will be equal to 0. So this is what we can say, it is the balance factor, and it is the AVL tree. So AVL tree, the property of your the binary search tree remains the same thing, and the balance factor of any kind of your the node should not exceed the range. The range is, it can be either -1 or 0 or 1. These are the possible values. I'll explain with different kind of your the scenario. So consider this example, like we have the nodes, that is 30, 10, similarly 56, and certain kind of your the nodes are being present. And you have to identify whether it is an AVL tree depending on the balance factor. So how to start the balance factor? In general, you'll be starting the balance factor with the leaf nodes. That is balance factor of 8, node 8 equal to 0, balance factor of node 12 is equal to 0, balance factor of node 64 equal to 0. That is what we can say in simple to start with finding the balance factor of this kind of the node. So node 12 is equal to 0 and balance factor of node 8 is equal to 0 and the balance factor of 64 leaf node, that 64 is equal to 0 because it does not contain any left subtree or the right subtree. And to the next level, you need to find the balance factor of 21 because there is one level down. And that is the purpose the height of this kind of the node 21 equal to left subtree equal to 1. There is one node. That is here for the 21, there is a left subtree. The height is equal to 1. And for node 21, there is no right subtree. That is kept as 0. That is 1 minus 0, that will be equal to 1. So for node 21, the height is equal to 1. In the same fashion, if you need to find the balance factor of node 10. So what is the height of node 8? That is, if you consider the left subtree is equal to 1 and the right subtree, there are 2 levels down, that is 2. That is 1 minus 2. So height of the left subtree is 1, height of the right subtree is equal to 2. So 1 minus 2, that will be equal to minus 1. So for node 10, the balance factor is equal to minus 1. If you recall about the balance factor, what are the possible values? That is the possible values of the balance factor in AVL tree. It can be either minus 1 or it can be either 0 or it can be 1. So the property is being satisfied in all up to now. That is we got the values 0, 1 and simply minus 1. These are the allowable values of the balance factor. So in the same fashion, find the balance factor of the node 56. So how to find the balance factor of node 56? Height of the left subtree. Do we have any left subtree? We do not have. That is 0. Minus, what is the height of the right subtree? Since there is one level down, that is 1 will be the height of the node 56. So 0 minus 1, that will be equal to minus 1. And that is how we can say the node 56, the balance factor is equal to minus 1. And coming to the node 30. So within your node 30, that is what is the height of the left subtree? That is 1, 2, 3. That is node 10, node 21 and similarly node 12. That is height of the left subtree is equal to 3. And what about the height of the right subtree? There are 2 nodes which are present towards to the right subtree. That is 56 and similarly 64, 2 levels. So 3 minus 2, that will be equal to 1. So the balance factor of your node 30 is equal to 1. And that is how we can say this is an AVL tree. As I mentioned, for AVL tree, it should be the binary search tree. The property of the binary search tree should be satisfied. And the values of the B should be between, that is minus 1, 0 and similarly 1. So if you consider this kind of the tree, it is the binary search tree. Take any node and whatever the values that are being placed towards to the left should be, will be less than this kind of the root node, and whatever the nodes that you keep towards to the right is greater than the root node. And as well, the other property, that is the balance factor of any kind of the node in your AVL tree should have either minus 1 or 0 or 1. Take 30, it is equal to 1. So if you look at this kind of the yellow colored values, it is within the range. It is either 0 or 1 or minus 1, does not exceed this kind of the range. And that is how we can say this is an AVL tree. This is the AVL tree. And take another example, like if you consider you need to identify the balance factor, and you should also identify whether it is an AVL tree or not. So how to start with? The same thing which I've explained. Start with the leaf nodes. That is node 9, node 17, node 27, and node 65. All these kinds of the leaf nodes has the balance factor to be equal to 0. Balance factor to be equal to 0. And when coming to the node 10, and you can easily guess what is node 10's balance factor. There is one level that is node 9 to the left subtree, node 17 to the right subtree. That is 1 minus 1. That will be equal to 0. For node 10, the balance factor will be equal to 0. And of course, the leaf node 83, the balance factor will be equal to 0. And coming to the node 29, what is the height of the left subtree? That is 1. minus what is your right subtree? 0. 1 minus 0, that will be equal to 1. Similarly for node 60, that is height of your the left subtree. What is the height of your the left subtree? There is no left subtree, that is 0. And what about the case of the right subtree? That is 1. So height of your the balance factor of node 60 will be equal to 0 minus 1, that will be equal to minus 1. In the same fashion, you can identify what is the balance factor of node 23. That is, there are 2 levels down, and whereas here also 2 levels down. So 2 minus 2, that will be equal to 0. And coming to the node 82, there are 2 levels down. That is, left subtree will be equal to 2 minus right subtree will be equal to 1. So 2 minus 1, that will be equal to 1. And similarly, coming to the node 58, that is node 23 as one level, node 10 as the another level, and similarly node 9 as the another level. So 1, 2, 3. So for node 58, the height of your the left subtree is equal to, that is 3. And what about the case of the right subtree? Go to the leftmost node. That is 82, 60, and 65. So 3. So 3 minus 3, that will be equal to 0. So this is what we can say about how to identify the balance factor of the AVL tree. And coming to the next one, that is in your next video, I'll be covering about the rotations. That is, I'll give an example of how does the unbalanced tree looks like. And to the next case, how to make this kind of the unbalanced tree to the balanced tree. That is, what are the modifications that has to be done. If you consider the modifications, like take for example, we need to perform left rotate, right rotate, or LR rotation or RL rotation. We call it as the single rotation and the double rotations, which will be covered in your next video.